today's topic of discussion is laws of motion. So when we are describing the motion, there should be some physical quantities which describe this motion of an object. So what are those physical quantities which are very fundamental in nature, which can be helpful to describe this motion? So those physical fundamental quantities are as follows. So the first one is the mass of an object. The second one is the length, which describes the dimension of the object. The third one is the time, the duration in which the object's motion is taking place. So these will be the three fundamental quantities which are not further divisible into any other smaller quantities, and the rest of the other things like distance, speed, which are really helpful to talk regarding the motion, arise from these three fundamental quantities. And how are they related with the fundamental quantities? So speed here is distance traveled by the object upon time taken for it to travel. So I can actually write this speed in terms of distance, which is a length form, in time in which the object has traveled. So this will describe my speed. So this speed is being derived from the fundamental quantities which are not further divisible. So since it's being derived from the fundamental quantities, these quantities are called as derived quantities. So these derived quantities in combination with our fundamental quantities can describe the motion of an object. So is this all which is required to know regarding the motion? No. We are also supposed to know the direction in which this motion is taking place. So what are those quantities or things which actually talk not only regarding the magnitude of something but also the direction in which they are proceeding? They are called as vectors. So what are these vectors? Vectors basically talk regarding the physical quantities which vary in direction but are constant in magnitude. So vector talks both regarding the direction and magnitude. So when I say my speed is 5 meters per second, my speed does not tell me in which direction am I moving. It just gives me the information that my speed's magnitude is 5 meters per second. And hence this speed, which does not give any information regarding its direction, it is called as a scalar quantity. So one of these things which a scalar quantity could be is distance. Since my distance cannot tell anything regarding the direction in which I am proceeding, so distance is my scalar quantity. And as I have already told, speed is also just giving me the magnitude. It's not telling me in which direction am I proceeding. And the quantities like mass and time as well are also not telling anything regarding the direction in which I am proceeding. So these quantities which just talk regarding my magnitude of a physical quantity are called as scalar quantities. So for my description of motion, I would require a combination of both scalar quantities and vector quantities. Apart from these two categories, there is also another category called tensors, which actually change in both magnitude and direction at every point in their motion. When talking about vectors, I said the magnitude is constant, but the direction keeps changing at every point of motion. But with the tensors, it is so happening that the magnitude also changes with the direction in which the motion is proceeding. So here there's a both change in magnitude as well as direction at every point. Till now, even in our 10th standard, we never spoke about something called as tensors, though we already know some of the vector quantities. So what are some examples of some vector quantities which are the counterparts of our scalars? So for distance, it is the displacement, for speed, it is the velocity, and a change in velocity is called as acceleration, which also has both magnitude and direction. So these having been established will help us to know the state of motion and the properties regarding it. So tensors is actually out of our scope. So we are not going to talk about tensors. So what's in our scope is a combination of scalar and vector quantities which would be helpful for us to describe a motion of an object. So let's come back to the topic of discussion, which is laws of motion. It was put forth by Newton. And how did this happen? So it resulted as a thought process of his apple experiment. Once what happened was, he was sitting in an apple tree and then he noticed that an apple is falling from a tree towards the earth. He started questioning that why should it fall towards the earth and not fly somewhere else? What is the reason for the apple being pulled towards the earth? So he thought there must be some reason behind this happening, but he couldn't explain it then. People before Newton, like Aristotle, a Greek philosopher, he thought was it is a natural tendency that a body would come to an equilibrium position like falling onto the ground. He thought it's a natural occurring. Any body would finally end up being in a natural state. But Newton, he opposed this notion of Aristotle, saying naturally this cannot happen. Any body cannot naturally come to a motion. So there should be some other phenomenon which is responsible for this occurrence. So what is that thing which is responsible for this action of an apple falling down from a tree towards the earth? So this is an external force which is coming from the earth's surface, and it is like a pull which is pulling the apple towards the earth. This particular pull is a force which is called as gravitational force. And since an apple is falling, there is a velocity which is acting at every point in this. So a velocity is increasing once it reaches the ground, and the acceleration, because there's been a change in velocity at every point, this particular acceleration is defined by Newton as gravity, which is actually pulling that apple towards the earth's surface. So the acceleration in this particular case is the gravity. So aspects like these have been picked up by Newton, and he started observing various physical mechanical systems around him. After a series of observation, he has come up with few laws which could describe the motion completely. So they are 3 in number, and now let's talk about it. So the Newton's first law talks regarding the concept called as inertia. So what is this inertia now? When I'm saying a body is set into motion, something might have resulted in this motion. So what this inertia says is, it is an inability of an object to move on its own, let it be stationary or let it already be set to motion. There is an inability in the object that it would move on its own. That is never going to happen unless acted upon by something external influence. Only if there is an external influence acting on that particular object will that object move, let it be stationary or let it be already set to motion. So this particular inability of an object to move on its own unless acted upon by an external agency force is called as inertia. So inertia is what is the first Newton's law. Where do we actually see this inertia if you talk about it? Imagine you're traveling in a bus. You just sat in the bus and the bus suddenly starts. So what happens? You jerk a little bit back. And why is that happening? Because you're already in rest and there is an external disturbance like the start of the bus, which is pulling you backwards because the motion has suddenly started. So this external agency is making you to move backwards. So this is something regarding the inertia at rest. So what about the inertia in motion? Consider the same case while you're traveling in bus, and to avoid an accident, a sudden brake is being applied. So what happens when a sudden brake is being applied? You move a little bit forwards. And why is that happening? It's because of the inertia in motion. So I told this inertia applies to both an object which is stationary and also in uniform motion. So this particular phenomenon of falling frontward when a brake is applied is because of the inertia of motion. Likewise, in various examples, you can actually see where inertia is acting. So this is all about the Newton's first law. Now what does the second law talk about? Now that you know that an external force is definitely required for some change in movement. So what is this change is being talked about in the Newton's second law. This Newton's second law talks about the force, which is a vector quantity because I said it depends on the direction in which the motion is proceeding. And what is this force and why is this happening? It's because of an external disturbance. And how is it changing the object which is in motion? By a mass times its acceleration. In short, mass is represented by m and acceleration, since it's a vector, I put a bar on it representing it a vector. So the formula for force which is external is mass times acceleration. So the external force is being balanced by a change in velocity in that object possessing some mass m. This is what you have learned till your 10th standard. So there is this other version of Newton's second law which you are new to. And to go about knowing that new version of second law, we have to talk about something called linear momentum. What is linear momentum? What is linear? Moving in a straight line. What is momentum? Pick picking up some velocity. An object with mass m picking up some velocity. That's called as momentum. So the formula for momentum is mass times its velocity. It's in short represented with a symbol P. So basically P is mass times velocity. Since velocity is a vector because it also talks about the direction in which it's proceeding, momentum is also a vector. So this linear momentum is another form of talking about the Newton's second law. And how is this force related to momentum? Force is basically a change in momentum over a period of time. Suppose let I say that I started off with a P initial, let's say P initial motion, and then at the end of the motion my momentum is P final. So a change is a subtraction between these two quantities. So how would I represent it? I represent it with a delta, which tells about a change. So a change in P, and then the time interval in which this motion happened talks about the change in time, which is represented by delta t. So in this change in time, how is my momentum changing? So this is another way of talking about the Newton's second law. So what it basically states is the external force being applied is directly proportional to the change in momentum of an object, and this change happens to be in the direction of motion. So if this is the direction of motion, then this change is also happening along this same direction only. So this is what the Newton's second law's another version, which is the linear momentum version, talks about. And how do we actually envisage this change in linear momentum? Let's take an example and see. So in this particular example, I take two blocks of different masses. Let's say the smaller mass is represented by a small m, and a bigger mass which is just connected to the smaller mass is represented by a small m. They are lying on a surface like a table, let's say. So when will this momentum change occur? Only when there is an external disturbance of force. So let me act a force onto it. So when I am applying a force on this small block m, because it is also connected with the capital M block, both will move together. So initially these both, since they are of different masses, and since we have already seen that linear momentum describes something which is related to mass, and here we have two different masses. So what do we actually see? At the start of motion, once I have pushed it, since the masses are different, these both masses will have different momentums because of their different masses. But what happens at the end of the journey? We observe that both of these masses, despite having different masses each, they land up having the same linear momentum. This is again a question. Why is this happening? So what do we thought previously? If there's a change in mass, so there should be a change in momentum. So what is this reason behind the change? Is it the masses of the objects itself? No, that's wrong. What's resulting here is the nature of the force which is acting on these objects, which is responsible for the change in momentum, and not the object's mass itself. So irrespective of what these masses are, they would end up moving with same linear momentum, and the change would be constant. So this is also given by dp by dt, which is common for both these masses. So this is how we can describe the Newton's second law in action. Now let's go to Newton's third law. So what does this Newton's third law talk about? what it basically says is, for every action, there's an equal and opposite reaction. What does equal and opposite mean? Consider me, I'm standing on the surface. So when I'm standing on the surface, my weight is acting onto the ground? Yes. So when I'm putting some weight, it's the force which I'm acting onto the ground. So in return, even this ground will exert some force towards me. So this particular force, which is in the opposite direction, is a normal reaction force. Why is the word normal being used here? Since I am standing perpendicular to the surface, perpendiculars, another way of saying is normal. So this reaction is happening normally to the surface, and hence this reaction is named as normal reaction. And what's the action here? My weight. Weight is the action here. And what is weight? It's mass times gravity. So this Newton's law basically talks about an action-reaction pair. It is quite essential that if Newton's laws hold, then the forces which are occurring out of Newton's laws always occur in action-reaction pair. If there is an action, there is definitely an equal and opposite reaction. So this is what is talked about in the Newton's third law. In the case where I was considering my weight acting downwards, it's the normal reaction, which is the reaction force which is acting onto me. So this is a reaction force, a type, and other types would be as follows. So the first one we have already dealt with, so that's the normal reaction. The second one is, suppose I have a horizontal surface and then I have a mass of mass m, let's say, and if I'm acting a force onto it in this particular direction, this would be my direction of net acceleration. Since it is sitting on this particular surface, the surface should act something when there is a movement. So there should be some force which should oppose this external force applied. So this opposing force in this case, which has resulted because of the nature of the surface in which this block is placed, is called as frictional force, and it is opposite to the direction of applied force. Frictional force, which is represented by small f. So second one is frictional force. Now, I'll take another example where there's another type of reaction force which is considered. Let me take an example of a pendulum. Let's say this is a bob which is attached to a spring to a ceiling. So obviously there's a mass or the weight of the bob which is acting downwards. And since according to the Newton's third law, for every action there should be an equal and opposite reaction, the reaction pair which occurs in the opposite direction to that of the action here is called as tension in the string. It is the ability of that string to hold that particular bob. That force which is holding it firmly against its weight in the opposite direction is called as tension, which is represented by the letter T. So tension is the third kind of reaction force which would be interested to know. So in coming chapters, we will be learning in detail regarding all these kinds of reaction forces. Thank you.